So, what am I going to call this section? I'm just going to call this section... It's a lot of chit-chat, but I don't think any of it's aimed at me. Div, not dive. Div, curl, and I see no reason why we shouldn't start Green's theorem. Green's theorem is really nice. Don't be scared of it because it's got capital letters in its name, okay? Green's theorem is actually really nice. It's hugely labor-saving. Green's theorem is lovely. Stokes theorem gets a little bit sticky, but Green's theorem is really, really nice. I think you'll like it. But to begin with, let's do curl and div. I'm going to do exercise 22. It says find the curl and divergence of f if f is this thing over here. So let me write it down. X e to the, oh, my old eyes. E to the y, j plus y e to the z, k. All right, which if you want to write it in parenthesis notation is that. Okay, so let's work out div of f. Div f is simply the derivative of 0 with respect to x plus the derivative of x e to the y with respect to y plus the derivative of y e to the z with respect to z, and that's our answer. That's pretty boring. And just in case you're wondering where all of that came from, and I think that's in a box, isn't it? Yes. Page 63, XDYD, ugh, no. I was just checking to see whether I'd fixed an old typo, and I had fixed an old typo, but there's a new typo. On the box on page 63, the very first thing is defining del, the differential operator vector, and there's a pretty obvious typo. It says d by dx, d by dy, d by dx. But it should be d by dz. I'm sorry. Ah, man. The typo that was there has gone away. But somehow I managed to substitute another. Okay, so in fact, let me just put that in here. Please note typo, page 63 box. I'm sorry about that. Okay, curl f. Curl f's not too bad. It requires slightly more work than div because it's or it's at least modeled as a cross product. So let me do that. So 0 x e to the y, y e to the z, and I've told you it's my habit to write the bottom line first because sometimes those component functions can be quite big and chunky, and then I want to make sure I've got them properly spaced. D by dx, d by dy, d by dz, d by dx, d by dy. Those are operators. They have no existence on their own. They only exist in their action on other things. So it's d by dx of something, d by dy of something. So strictly speaking, this is not a cross product. It's a cross operation, I suppose. All right, so what's curl f? It'll be d by dy of y e to the z minus d by dz of x e to the y. Then d by dz of 0 minus d by dx of y e to the z. And then d by dx of x e to the y minus d by dy of 0. There we go. Oops. And that's a 0, and that's e to the y, and there's curl f. Okay, so at the moment all we're really doing is just practicing doing the calculations rather than using these in a context. Exercise 23, we're given a scalar function. Okay. And we're told to find the vector field that is grad f. Okay, well let's do that. the derivative of little f with respect to x, the derivative of little f with respect to y, the derivative of little f with respect to z. Okay, that's grad f. So big F is obviously a conservative vector field because there exists a little f such that big F is grad of little f. That's how we got big F. Okay, so big F is clearly a conservative vector field. Little f is its potential function, or is a potential function for big F. And now in B we want to find curl of big F. And remember those two theorems I ended with yesterday? It said that curl of grad F is 0. Well, let's see. Let's actually... obviously you can't prove something with an example, but you can at least kind of convince yourself that maybe there's something to it. So let's work out curl F. 2x plus 3yz, 3xz, 3xy. You do cross product whichever way makes you happy. Everybody's got their own little funny ways of writing cross products. Some people memorize the formula for cross products. Sure, I don't have enough brain space for that. Okay, d by dx of that would be 3z minus d by dz of that would be 3x. That can't be true. Where have I made a mistake? D by dx of that. I've made some careless mistake. Where is my careless mistake? I should be getting 0 before I go further. Can anybody see it? Otherwise I'll just look up in my notes. I'm supposed to be getting 0, aren't I? Am I going mad? Could be going mad. I don't think so. Of course, mad people never think they're going mad. I think that's one of the characteristics of going mad, isn't it? Okay, my notes are completely useless. They just say curl F is 0. 2x plus 3yz, 3xz, 3xy, 2x plus 3yz, 3xz, 3xy. Oh, I see. That one's in the wrong place. That's the one I want. 3x, there we go. I was just getting my cross product wrong. I thought I got my components wrong, but I was just doing my cross product incorrectly. Okay, let's try the j term. D by dz of that would be 3y minus d by dx of that is also 3y, and d by dx of that is 3z minus d by dy of that is 3z, and altogether we simply end up with the 0 vector. And you can reliably expect that. The curl of grad f is 0. In other words, the curl of a conservative vector field is 0. And that's the trick for working out if a vector field is conservative or not. Before, when we first encountered it, I said which of these three is conservative, and then we kind of figured it out by inspection. But if you work out curl, then you can see the ones that have a non-zero curl are not conservative. Okay, why don't you give number 25 a go? 24 and 25. 24, simply calculate div and curl just for some practice. 25, figure out which of those big F's are conservative by working out their curl. And then just as dessert, figure out what their potential functions are. So off you go. You try 24 and 25. Just a note about this triangle notation. Come on, stylus. If we put that in front of a little f, it means the gradient of a scalar function. Okay? And it's going to be d little f by dx, d little f by dy, d little f by dz. Okay? But if we put that triangle in front of a vector field, what I've written now doesn't make any sense. You can't have grad of a vector field. So you've got to have that symbol in between, and of course there's a choice of two symbols. Okay? And then that top one is div, and that bottom one is curl, and you get the one with what looks like a dot product, and the other one what looks like a curl, what looks like a cross product. And this will give you a scalar function, and this will give you a vector function. Okay, and so that little triangle is used, we've used it in 3 senses now. When we're applying that little triangle symbol to a scalar function, we typically use a lowercase f, and we don't have a dot or a cross. All right, and the thing it produces is obviously a vector function. So be careful of that little triangle story. If you're putting it in front of a scalar function, you don't need a dot or a cross, and the thing that you get out of it is a gradient vector. If you're putting that triangle little symbol in front of a vector field, which we typically denote with a capital letter, then you have to choose between which of those 2 things you're doing. Is it a div or is it a curl? And you represent them with different symbols. And you don't actually have to use that triangle symbol ever in the context of these last 2. You could just write div f and curl f and actually never use that triangle symbol. Green's theorem. Okay, first of all, one of Tracy's pet peeves, where to put the apostrophe. This is named for someone whose surname is Green. Therefore, the apostrophe S is possessive, and it's Green's apostrophe S. Okay, cool. Right. Stokes theorem is named for someone whose surname is Stokes. There's already an S in the surname. The apostrophe comes after the S. So when we hit Stokes theorem, there's the apostrophe. You lot are clever enough to do multivariable calculus. You're clever enough to know where to put the apostrophe. Okay? Okay. I will not subtract a mark if you put the apostrophe in the wrong place, but I will be sorely tempted. But I won't. Okay, Green's theorem. So, Green's theorem is essentially a scaling up of the fundamental theorem of calculus. What the fundamental theorem of calculus does, and I will write this down, but first I'll talk about it. What the fundamental theorem of calculus does is it relates the integral of a derivative of a function to the actual values of that function on the endpoints of your interval. Think about fundamental theorem of calculus, and then you're thinking, I know I've heard those words before, but I can't remember what it is. It's what you're using whenever you do an integral and you ask yourself, what did I differentiate to get this integrand? And then you figure it out and you write it down and you put little square brackets and you write a and b and then you substitute in. You're using the fundamental theorem of calculus when you do that. Because you're looking at your integrand as the derivative of something. It's a derivative of a function. And then you're seeing that you're integrating the derivative of a function, and then the result of that integral is the difference between the value of that function, of that antiderivative, at the endpoints of the interval. So Green's theorem, Stokes theorem, and divergence theorem are basically just stepping up in dimensions the fundamental theorem of calculus, where you're still looking at the integral of a derivative, except it'll be the double integral of a derivative, or the surface integral of a derivative, or the triple integral of a derivative, and you're going to equate that integral of a derivative with the value of a function at the edges of the interval, except it's not edges of the interval now, because a double integral is on a region, and the edge of your region will be a curve. Okay? A surface integral involves a surface, and the edge of your surface is once again a curve, a space curve. And a triple integral is always evaluated over some 3D solid, and the edge of your 3D solid is a surface. Okay, your phone isn't going to write your exam for you. Please put it away. So what we do in each of these things, Green's, which is about double integrals, Stokes, which is about surface, and triple, which is about divergence theorem, also called Gauss's theorem, which is about triple integrals. In each case, we're going to be taking that integral and not so much evaluating it, not so much just function values, but essentially stripping away one integral sign, in a sense. So double integrals can become line integrals, surface integrals can become line integrals, and triple integrals can become double or surface integrals, two integral symbols. Okay, all right. So after all that chit-chat, let me do some writing. But that's the basic idea. So fundamentally, what we're doing here is we're taking the fundamental theorem of calculus and stepping it up by a dimension or two. And if you look in one of the chapters in your textbook, there's a rather lovely box right at the end of the chapter. I don't know which chapter. If Greens and Stokes and divergence are all in the same chapter, it'll be that one. At the end, there's a nice box where they give you just the formula and a picture to show you how single variable fundamental theorem of calculus, line integral, double integral, surface integral, triple integral, how they all are members of the same family. It's a very nice sort of informative box somewhere at the end of a chapter. Okay, the fundamental theorem of calculus describes a relationship between an integral of a derivative of a function and actual values of that function. And the primary result of the fundamental theorem of calculus looks something like this. Could you please keep quiet? Okay. We ask ourselves, what did I differentiate to get that integrand? Answer would be little f, and then we evaluate little f at b and a. Okay, the three great theorems, perhaps my enthusiasm is showing there, the three great theorems of vector calculus take the same form relating a double or surface or triple integral of a derivative. I'm basically trying to write this sentence so that it kind of looks like the previous sentence, if you can see what I'm doing there. Of a derivative of a function across a region with something related to the value of that function at the edges, the boundary of the region. Okay, and that applies to Green, Stokes, and divergence. Of all of these, Green's theorem is the simplest, and in fact, Green's theorem, we will later show, is a special case of Stokes' theorem. Green's theorem is the simplest of these three theorems. Okay, all right. Now what I'm about to write is in that box on page 65, so you can copy it down if you want, but it is word for word exactly what's there. Green's theorem in words is, let C be a positively oriented, we know what that is, piecewise smooth, meaning it can have corners, but it needs to be smooth in between those corners. And don't worry, mathematicians can think of functions that have no smooth bits at all and in fact consist entirely of something akin to corners. Piecewise smooth, simple closed curve, we know what that is. In the plane, so in the xy plane or whatever you're calling your coordinate axes. And let D be the region bounded by C, if P and Q have continuous partial derivatives, so they're functions, have continuous partial derivatives on an open region that contains D. That's mathematics speak. Then what do we have? We have this great and wonderful formula which you're going to have to memorize, which is this. Okay. It's a double integral of a derivative, except derivative is becoming a slightly more complicated concept than simply f dash. But it's the double integral of a derivative, and we are equating it to something along the boundary of D, where the boundary of D is C. Notice C is not a space curve. It's a curve on one of the coordinate planes. So this is a double integral, not a surface integral. Yeah. There is a proof of Green's theorem. I am not going to cover it. It is in your textbook. Yeah, so I'm giving that to you without proof. If you prefer to see proof so you can see where it's coming from, then I applaud you, and the proof is in your textbook. We just don't really have time. The proof would take a lecture. It's not one of those ones that's quick and easy to prove. Yeah, what is there to say about that? Let me talk about that open region. It basically means that P and Q need to be nicely well behaved across the region, and also for at least just a little bit outside the region. P and Q can go completely crazy somewhere else, but long as they've got nice derivatives and everything within the region D and just a little bit outside it, that's what that open region containing D means, then everything's cool and this formula will work. Question?
When we say piecewise smooth, are we saying that it's like differentiable, or what is that?
It means differentiable, yes, and it means that it's differentiable in pieces. So corners are okay, like a square, which isn't differentiable at its corners, but it is differentiable in between, so you could piecewise define it, and each of those pieces would be differentiable. It basically means that you have to have a finite number of pieces. It looks like that's something that doesn't have to be mentioned, but for this to be a strong formula, a strong theorem that can withstand all sort of special cases, that wording has to be there. Question?
So just thinking, if like one of our functions say where like the absolute value of x, because it's in two finite pieces, would that mean
it's still piecewise smooth? Yes. So mod x is piecewise smooth. Yes. Okay. Okay, I've got in my notes here, it says here, a few notes on notation. So let's get that out of the way, and then tomorrow we can jump into examples. A few notes on notation. Because C is necessarily a closed curve, because it's the boundary of a region, being the entire boundary of the region D. Instead of writing just the integral sign with a C at the bottom, we can use that symbol that we've already seen that's got the little ring on it to show it's a closed curve. We can also write the line integral symbol as, okay, I've shown that to you before. It's got a little ring on it just to show that C is a closed curve. Okay, so there's one little note on notation. Here's another. The boundary of region. Okay, this is just going to, I'm afraid this is possibly going to confuse you because it's a new use of a symbol that you've already seen in other contexts. The boundary of region D can also be called, or be called is not really the right term here. It's just a symbolic thing, symbolized as that instead of giving the boundary of a region its own name, like C, and introducing a new symbol into the mix, if you've got a region and you want to talk about the boundary of that region, you can just put that little curly D in front of it, and it means the boundary of the region. And that way you don't need to give the boundary of the region its own name. Instead of giving it its own name, like C. So you might come across that notation somewhere. And then I've got one last thing. Okay, it's not actually notation, so I shouldn't really be doing it as a bullet point. The most obvious use so now the equation for Green's theorem has a double integral on one side and a line integral on the other side, and you can use Green's theorem in either direction. You can turn a double integral into a line integral, or you can turn a line integral into a double integral. You can do it in either direction. And the most obvious use of Green's theorem, or the most typical use of Green's theorem, is to turn line integrals, which are often harder to do, into a double integral, which are often quite easy to do. But we do it the other way as well, depending on the context, usually, but not always. The line integral is harder work than the associated double integral. Harder work than the associated double integral. Okay, so first thing tomorrow I'll do exercise 29, which is all about turning line integrals into double integrals. And then you'll give number 30 and 31 a go. So that's what we'll do tomorrow, and yeah.